Hi guys, Kieran McAvoy here from A Clever Chimp, and on this channel we talk, learn and discuss about maths, physics and all things engineering. This video is part of our guide to engineering maths, and today we're going to be talking about determinants, why they exist, where they originated from, and how we can understand what they have to do with a 2D transformation today. All of that is coming right up. So far in our understanding of matrices, we've seen how we can put a pair of simultaneous equations into matrix form in the idea of transforming a vector onto another vector. And that gave us a way in which we could visualize a unique solution, no solutions, and an infinite amount of solutions. But is there something about either the equations or the matrix that could tell us whether or not there was going to be any solutions in the first place? Well, that's where the idea of a determinant comes in. Let's take these two general simultaneous equations. Ax plus by is equal to some number m, and we have cx plus dy is equal to another number n. Now what we want to try and do is eliminate one of the variables, and we're going to eliminate the x variable first, okay? So we're going to times the equation 1 by c, and we'll times the equation 2 by a. So we'll have acx plus bcy is equal to mc, and acx plus ady is equal to na. Now, what we can do now is we can do equation 2 minus equation 1, and we're left with ady minus bcy is equal to na minus mc. And if we factor out the y, then we're left with AD minus BC multiplied by y is equal to NA minus MC. Let's go a little bit further now and divide through by AD minus BC, where we have y is equal to NA minus MC all over AD minus BC. So looking at this, we have our variable y that is only going to exist, that will only exist if the denominator on the right hand side, AD minus BC, is not equal to 0, because if it is, then this falls apart. It's impossible. This equation does not work. And before we get to the punchline and just name this AD minus BC the determinant, let's work out it for the x value, just so that we're all above board here. Doing the same sort of thing for the x value, we're left with the same situation. We're left with x is equal to md minus nb all over ad minus bc. So let's have a look at what that looks like in matrix form. We have our generic matrix A, B, C, D, pre-multiplying our vector xy, and that'll equal some vector, some transformed vector on the right hand side. But what's important to notice here is the way in which we've worked out whether there's going to be a solution or not, whether there could possibly be a solution or not, is all dependent on the elements of the transformation matrix, A times D minus B times C. And so that is a determinant of a 2 by 2 matrix. It is determining whether or not there is going to be solutions to the equation. Now, if you're like me, you'll be sat there thinking, well, why didn't we minus the equations the other way around and be left with BC minus AD? And why don't we call that the determinant? I've had the same thought. Honestly, I've had the same thought. And I looked and tried to research whether there had been any answers to this, but I couldn't actually find anything online. But I will get to the reasoning as to why I believe that it has to be AD minus BC for it to all match up with the idea of transformations and other equations. But we'll get to that as we develop our understanding in understanding the determinant, what that means in terms of transformations, which we'll move on to next. So let's start off with our 2D plane, and on that plane we have the unit square, with the corners being defined by the vectors 0, 0, 1, 0, 0, 1, and 1, 1. So what we want to do is we want to transform each vector by a matrix. Let's say that that matrix is -1, -5, 3, and 1. Now I will prove it in a later video, but we can understand the determinant of this matrix, of any matrix, in terms of two-dimensional space, to be how much the area is scaled by after the transformation. So you start with a shape of area 1 unit squared, and the determinant will tell you how much the area is scaled by after the transformation. So knowing what we know about the determinant now, let's work out the determinant of this matrix. We have A times D, which is -1 times 1, minus B times C, which is -5 times 3. And that equals 14. So that means that the area that we're expecting in our new shape is going to be 1 unit squared times 14, being 14 units squared. So let's watch as our unit square is transformed. As you can see, we've got a bit of rotation going on, we've got a bit of shearing going on, and it's getting bigger as well. It's turning into this larger parallelogram. The area of that parallelogram is equal to 14. And like I said, I'll do another video on the proof of this fact later on, but for now, let's move on to thinking about what a negative determinant would mean. Hopefully this negative determinant situation will shed some light on why it's AD minus BC as opposed to BC minus AD, because minus AD minus BC is equal to BC minus AD. So what we'll do is we'll start off with our transformation matrix, -1, -5, 3, 1, and what we'll do is we'll do a row swap, okay? We'll do a row swap, so we're left with 3, 1, -1, -5, okay? And what you might notice now is that our C and B are on the leading diagonal, and our A and D are on the other diagonal. And so if we were to work out the determinant on this in the same manner as what we had done with the equations, then we would have 3 times -5 minus 1 times -1, which would leave us with -14. Let's see what that means in terms of transforming space now. Let's apply that transformation matrix on our unit square. What I want you to do is watch where the I hat and j hat vectors are initially, and watch where they land afterwards. As you can see, the whole of 2D space has been flipped. An easy way to understand why the 2D plane is flipping is to use your fingers as a coordinate system. Let's say that my index finger is I hat, my middle finger is j hat, and my thumb is a third vector perpendicular to both of them, commonly called k hat. Before we did the transformation, we had our unit square, with I hat clockwise of j hat across the smallest angle. Now after the transformation, I hat was anti-clockwise of j hat, and the only way that that is possible is if the coordinate system flips. Now you see that I hat is anti-clockwise of j hat over the smallest angle. And we have our thumb, k hat, pointing down now. So the whole coordinate system has flipped. So it's clear from that understanding that our original transformation matrix transformed the space and kept everything upright. My thumb would have been pointing towards you all the time. But the transformation matrix, after doing a row swap, giving a negative determinant, has flipped the whole of two-dimensional space. The important part to understand here is that the determinant of a matrix needs to match up with the actual transformation the matrix is describing. If when working with our original matrix we calculated the determinant using BC minus AD instead of AD minus BC, we'd have expected space to flip, and would have been rather shocked when it didn't. So I hope that gives you some reasoning as to why the determinant of a 2x2 matrix is AD minus BC as opposed to BC minus AD. But I'd love to hear what you think. I really honestly would love to see if anybody finds anything to do with this, and see whether there's another reason as to why we have to have it as AD minus BC as opposed to the other way round. Now moving on, what happens when the determinant is equal to 0? Well, let's use one of our matrices that we looked at in our previous videos. We have 2 minus 1, 4 minus 2. So let's start off with our unit square and watch this transformation. So as expected, it has completely squished that area, that two-dimensional area, down to a singular line. And so that is kind of where, actually, it kind of makes sense with the fact that the determinant is equal to 0, because if the determinant is equal to 0, then we're scaling that area by 0, which in essence is just squishing it down to nothing. But is there something else that this determinant equaling 0 is telling us about the system? Well, what if I was to ask you what the original shape was? What if I was to give you this squished space of one-dimensional space and ask you what the original shape was? Well, you wouldn't be able to tell me, would you? You wouldn't be able to say, oh, well, that was a unit square, or that was a cloud shape over here, or it was a triangle over there and it just got squished down to this space. You wouldn't be able to tell me that. And that is saying that there is no transformation. There is no transformation that we could transform this one-dimensional space into a two-dimensional space back to its original state. In essence, it's telling us that the matrix that we transformed the two-dimensional space originally with down to this one-dimensional space does not have an inverse. More on that in another video. So thanks very much for watching, guys. I hope this video has helped you understand where the idea of a determinant originates from and helps you understand what a determinant means in terms of transforming two-dimensional space. If you like the video, then do us a solid and leave us a thumbs up. And remember to subscribe to the channel if you want to see more from A Clever Chimp, if you want to keep up to date with any new videos coming out from A Clever Chimp. So thanks very much for watching, guys. I will see you all in the next video. Bye-bye.